right, everyone. We're doing section 4.5, which is the last section about Laplace transforms, and we're going to be talking about Laplace transforms for Dirac delta functions and periodic functions. So we're just going to recap the meaning of the delta function. I tried to introduce it to you in our last set of videos to kind of set the stage for this, and we're just going to talk about it one more time. You might want to write down in your notes this right here in the same place you've been writing down all of your Laplace transforms every time I tell you to. This is the one for the Laplace transform of the delta function, so it'll come up again. We'll do some examples with that, and then we'll talk about periodic functions. So you might want to also copy down this property in that same place where you've been keeping your record of Laplace transforms. You should have at this point like a single table that you can refer back to solve any problem using Laplace transforms, and that'll be the complete list of properties of Laplace transforms that we use on like your upcoming exam. So about delta functions. These are going to come up in your project, so please do pay attention. Just remember that we talked about this last sort of class or set of videos, but the Dirac delta function is a special function. And we denote it some delta of t minus t0, and that's always going to mean a function that's infinity when t is equal to t0 and 0 otherwise. Another property of the delta function is that the integral of it from 0 to infinity with respect to time is going to be 1. And it emerges a lot in physical applications. So it acts like a pulse at t0. We kind of drew some pictures last class where it looks kind of like this, kind of going off the page actually at this point, kind of like up to infinity, and then coming back down, and that jump happening only at t0. And we talked about how you could think about it as the approximation of increasingly thin rectangles that approach a rectangle that's infinitely thin and infinitely tall. So it can be thought of as a piecewise, well, I don't have room for that, piecewise constant function over increasingly narrow intervals. That's that limit idea that we talked about last class. And everything else about the delta function, it acts kind of like a normal function would. So let's say like we've got delta of t minus 8. So that's going to, right here at 8, do that thing. If we had delta of t minus 4 plus delta of t minus 8, what that's going to look like is, you know, it does its thing up at 4, and then it does its thing again up at 8. And so it just, it acts that way. So you can take sums and scalar multiples of delta using the same rules you would for other functions. And then most important for us is going to be, actually I'll do a little arrow, or stars, I guess. That property I told you to write down on the first page, the Laplace transform of this function, is that delta of t minus t0 has the Laplace transform e to the minus st0. And since Laplace transforms take in functions that have 0 or higher input for time, that really only makes sense for t0 greater than 0, as I wrote here when I told you to copy it down originally. So that's what we need to know about delta functions. And we're just going to work through a couple examples because we'll be dealing with these in your project. So we want to make sure we have a good feeling for this. Let's do the function for delta of t minus 2 pi. We're going to go ahead and take that Laplace transform, and then in our next example, we'll actually make that part of a differential equation after we've just made sure that we know how to do this. So the Laplace transform going forward of 4 delta of t minus 2 pi is just going to be 4 times the Laplace transform of delta of t minus 2 pi. Oh, great. My pen is just all over the place. Delta of t minus 2 pi. And so here we have a delta function, just our t0 is 2 pi. And so we can go back to that property. It's e to the minus st0. So equals 4e to the minus st0, where t0 we just found out is 2 pi. So you just make that replacement. So 4e to the minus 2 pi s would be the answer right there. And then what we're going to go ahead and do is, in our next video, we'll turn this into a differential equation problem. So let's go ahead and write that right now. This is 4.5. Oh, great. 4. Well, it's weird that it never wants to write the words, but it's happy with my frustrated scribbles. So 4.5.1 is this initial value problem, y double prime plus y equal to 4 delta of t minus 2 pi, with y of 0 equal 1 and y prime of 0 equal to 0. And we're going to solve this problem in the next video, but I want to kind of introduce to you why we're thinking about it. So if you remember from when we were working during exam 2, y double prime plus y equal to some stuff is a thing that you could have solved using constant coefficients, and it actually looks like an undamped spring with some kind of forcing term, in this case for delta t minus 2 pi. And when I say it's an undamped spring with forcing term 4 delta t minus 2 pi, it's not like we've been told that for this problem, but that's what it looks like. Remember, your spring equations were like x double prime plus beta x prime plus x equal to f of t, like that. So here's our kind of like kx term. And then we're just missing this middle term for damping. And the reason I want you to be thinking about that is because it gives you intuition for how this should behave. The forcing term on the spring is just a single pulse, basically. It's just one big push. Oops. When, that's not how you spell when t is equal to 2 pi. And so you imagine you have the spring that would run normally, and then when t equals 2 pi, for some reason, you just shove it really hard. And that's the physical idea of this equation that's in front of us, even though it wasn't told to us as a word problem. And so, and nothing else. So between now and the next video, maybe think about what you think a solution will look like, and then we'll proceed with the solution from here.